All right, then I will start the recording. Thanks, Irene, for reminding me. Yeah, and now you can start.
Okay, thank you very much, Eduardo, for the introduction. And let me start by thanking all the organizers for putting together this wonderful seminar series and, of course, for giving me the opportunity to speak. So today I will present some work I did together with my supervisor, Thomas, and also a fellow student, Damian. And it's based on a paper which we wrote over a year ago now, but yeah, I wanted to take this opportunity to sort of talk about it, give you a slightly up-to-date perspective on this, and also just, to get to introduce myself to the community, because probably many of you don't really, well, have not really seen me yet. So let me start with some words of motivation and also introduce sort of the main playground where the talk will take place, which is asymptotic Hodge theory. So this is about studying variations of Hodge structure over a moduli space M. So a Hodge structure is nothing but some decomposition of a vector space H in terms of various pieces which have some complex conjugation property. And a variation of this just means that if at one point you have these subspaces, then as you move over the moduli space, the orientation of these spaces changes. That's sort of what I've tried to depict here in this drawing. So of course, this is not just some mathematical fantasy, but these spaces of this structure actually appears naturally in string compactifications. So the guiding example I would like you to have in mind is that of type 2b or F theory on a Calabi-Yau manifold. In this case, this moduli space M is just the complex structure moduli space. And this PQ splitting is just a splitting of a harmonic form in terms of its degree P, Q. Now, the reason we care about this splitting is because it tells us a lot about the effective field theory, right? So for example, this splitting contains information about the period vector. So it tells you about scalar potentials, about the field space metric, about masses of PPS states, and so on. So it's useful to know something about this decomposition, but in general, this is very hard. And this is where the word asymptotic comes in. So as most of you know, probably in string theory, we are often interested in considering regions of the moduli space that are close to the boundary. These are the asymptotic regions. And there are multiple reasons for this. The first one I already alluded to, which is computational control, right? Often these limits may correspond to having some weakly coupled EFT or some suppression of large volumes. And the second reason is that often in these limits, Swampland conjectures become relevant, in particular things like the distance conjecture, because you might have traveled an infinite distance to get to these boundaries. Now, I think it's fair to say that over the past years, asymptotic Hodge theory has been very successful in helping us answer all kinds of questions in this regard. I'm not going to even try to give you a full list of all the references. For this, you can look at any of our papers. So I would say the reason this program is successful is because it allows us to look at simpler things. What it gives us is a successive approximation scheme for this full splitting in terms of simpler things. So for example, if you are content with dropping exponential corrections, you are in the so-called nilpotent orbit approximation. And if you go even coarser, if you drop subpolynomial corrections in some appropriate hierarchy, you end up in the SL2 orbit approximation. And there's even a way to make sense of sort of getting rid of all the coordinate dependence and associating some Hodge structure really to the boundary. This last step is actually quite non-trivial, and it really makes use of all this asymptotic Hodge theory stuff. But what sort of makes the whole system work is that what emerges is a picture in which to each boundary you get to associate a simple set of data. So this boundary Hodge structure, some kind of SL2 algebra, and some special operator which we call the phase operator. And then from this boundary data, you can, for example, immediately write down this SL2 orbit approximation. Now, what I'm going to tell you in this talk is that you can actually go back even further. So there is a map which takes you from this boundary Hodge structure all the way back to the nilpotent piece. This map we will call H, and it's the period map. And this is quite remarkable because already in this nilpotent piece, this contains usually already some non-perturbative corrections. And sort of the thing that makes this work is you can imagine that this map needs to somehow respect this boundary data that you get when you go through this diagram. So if you like, the commutativity of this diagram restricts this map. And in fact, the map is so restricted that it is determined uniquely and algorithmically in terms of this boundary data. And this is sort of the seminal work of this paper of Kaplan, and Smith. But in sort of a true mathematician's sense, what they do is they give you an algorithm to compute it, but then 40 years later, no one actually ever went through this algorithm. So this is sort of the main contribution of our paper and what I want to show you in this talk, that you can really go through this procedure in examples and sort of do what we call a bulk reconstruction procedure of this age. So you can really reconstruct the nilpotent piece from just this boundary data. Now, at the same time, I want to emphasize in this talk that sort of this formulation of asymptotic Hodge theory is somewhat very physicsy, and I hope that this will become clearer as the talk progresses. But for example, if anyone is interested in getting into this Hodge theory business, but is a bit intimidated by all of this mathematics of limiting mixed Hodge structures, and I think this perspective could be very useful, and I think there's still much to explore here. Okay, so that concludes my general introduction. I will now proceed and give you some more details about what this period map actually is. But before that, let me just give some preliminaries. So for simplicity, I will assume that we have only one modulus, so one complex structure modulus. I will denote it by T. Its real part is X, its imaginary part is Y, and the asymptotic region that we are considering is where Y is large. Okay, the suction is large. This is just, I make this assumption for simplicity. In principle, everything I say can be generalized, but things just become much more complicated. The second thing I will do is I will actually look at polarized Hodge structures. So that just means that I have some bilinear form on my vector space, which has some nice properties. But for us in Calabi-Yau settings, you can just think of it as being given by this formula. And finally, I will introduce the symmetry group of this polarization. These are just the transformations that leave this invariant. And sort of in the standard Calabi-Yau threefold setting, this will just be the symplectic group. And so in particular, in the one modulus case, this is just SB4, right? H2,1 will be 1. So you can just think of very concrete groups in the back of your mind. Okay, so now let me introduce this period map properly. So here I've drawn sort of an abstract space of all possible polarized Hodge structures you can have of some given vector space. And now let's just pick one point here, and we call it a reference Hodge structure. Then it's quite easy to show that if you have any other Hodge structure, depending on some coordinates x, y, then there is a map that goes sort of between them. So this map I call H, and it will be a real group valued field. So it will be valued in this group I just mentioned. So it satisfies this equation, and the way you should read this equation is really H is some matrix which is going to act on the basis of this vector space, and then it gives you basis of this other vector space. Now, immediately from its definition, you can see that this map enjoys what we would call a gauge symmetry, right? If you multiply H from the right by some element V, which lies in the stabilizer of this reference Hodge structure, meaning it's just leave this, it doesn't move the point, then this equation stays the same. So really what you should do is you should think of this map as being a map from a moduli space to this coset G mod V, where the symmetry has been modded out. And this is what is known in the math literature as the period map. So as you see, the definition of this map depends on the choice of reference Hodge structure. And this is a bit awkward because it's a vector space. So to sort of remedy this, what these people did is they introduced what is called a charge operator, or what we call a charge operator. And it's very simple. It's just defined such that these HPQ spaces correspond to its eigenspaces. So an element V in HPQ is an eigenvector of this Q. For example, elements in H30 will be said to have charge 3/2. And this Q will actually be some element of the complexified Lie algebra of the group I introduced. And in a similar way, you can look at operators, so elements of this Lie algebra that act on the vector space. And you can get a charge decomposition of these operators depending on, what is their commutation relation with Q. And just to put this more into a picture, here I've depicted again this Hodge decomposition. Again, the H30 piece will have charge 3/2, the 2,1 piece has charge 1/2, etc. And then all we mean by an operator having charge -1, it just means that it maps elements in H30 to H21. Okay? And similarly, an operator which has charge 0 will just stay within the same PQ piece. Now, why do I introduce all this? Well, it turns out that this period map actually has a very particular charge decomposition. And this is referred to as the horizontality condition. So what is it? What you do is you look at sort of the Monnee-Cartan form that you build from this H. This will lie in the Lie algebra. And you can look at its holomorphic and anti-holomorphic components. Okay. And what you find is that this can only have a charge 0 piece and a charge ±1 piece, depending on whether it's holomorphic or anti-holomorphic. So it cannot have a +-2 piece, no +-3 piece, etc. So this is quite a stringent condition. And actually, you probably all know this relation, but in a very different way. So you all know that if you take the holomorphic 3,0 form and you take a holomorphic derivative, then you end up in H30 and plus H2,1. So this is saying that taking a holomorphic derivative can either keep your charge the same, which would correspond to this piece, or it can lower your charge by 1, which corresponds to this piece. Okay? So this horizontality condition essentially leaves us with 3 different charge components. So there's the plus piece, there's the minus piece, and then in principle, there are 2 0 pieces for the plus derivative and the minus derivative. But you can set these equal by a gauge transformation, precisely this gauge symmetry that I mentioned earlier. So at this point, we have now gauge fixed this symmetry. And I would denote these components by L+, L0, and L-. So now I will make one assumption. So I will assume that this period map has, let's say, a continuous shift symmetry. So meaning if I shift the axion by a constant, then all that changes is that I get an overall monodromy matrix in front of it. Okay. And this is sort of motivated by the fact that in the nilpotent orbit approximation, you have this symmetry. So if you assume this, then you can play a bit with these equations, and you find that these L+, L0, or L- satisfy a very nice set of equations called Nahm's equations. Okay, and the reason these are useful is because they don't involve this reference charge operator anymore. They only involve the L's. But I want to emphasize that these equations are weaker than this horizontality condition I mentioned. Nevertheless, sort of in the rest of the talk, what we will do is we will try to solve these equations first, and then we end up later imposing the rest, and this will be easier to do. So just as an aside, these Nahm's equations have a very nice geometric interpretation. So you could think of the moduli space, which is just this upper half plane, as being somehow, let's say, the world sheet of a string. And this map H is just an embedding of this string world sheet into this coset space. And then these Nahm's equations, what they say is they arise essentially from extremizing the area of the string world sheet with respect to the so-called Hodge metric, which is a natural metric that arises here in this target space. And it sort of also recently prompted this ideas of both Jacotti and by Thomas to formulate sort of all this Hodge theory business in terms of some auxiliary field theory on the moduli space, whose equations of motion precisely give you sort of this Nahm's equations. But, well, you now know that this is not a complete picture, because as I told you, these Nahm's equations are not the full story. The full story is this horizontality condition. And so late last year, Thomas and I wrote a follow-up paper on this, where we showed that if you want to get the full horizontality condition, you need to look at something called a lambda-deformed Wess-Zumino-Witten model. I won't say anything more about this today, but I want to advertise that I will hopefully give a parallel session talk about this at String Pheno. So if anyone is interested, I invite you to come listen then. Okay, but for the rest of the talk, I will leave this field theory picture behind. So just to summarize, I introduced for you this period map, which is just an alternative way of packaging the information that's in a Hodge structure, in this variation of Hodge structure. And I wrote down a bunch of differential equations that we now want to solve, essentially. But to solve this in general is very difficult. So what we are going to do is we're going to try to solve them near the boundary. Okay. So we are going to make essentially a series expansion around the point where y is large. So let's first look at sort of the leading term that you get here. So the leading term I will call normal L alpha. And if you plug this into Nahm's equations, you will find that these L's satisfy an algebra, which hopefully you all recognize as an SL2 algebra. So remember in the beginning, I said that one of the pieces of boundary data is an SL2 algebra, and sort of this is one perspective of how you can see this SL2 algebra emerge. Okay, and in fact, it's a very special SL2 because it also needs to satisfy this commutation relation with Q. These are referred to as horizontal SL2s in the maths literature. Now, the reason this is very nice is because, as you can see, the operator L0 here commutes with Q. So that means that you can find a simultaneous eigenspace decomposition, and this can give you a lot of structure, and we will do this in a moment. So just as an aside, what I mentioned in the beginning for boundary data was an SL2 triple that involved n plus, n0, and n minus. And these are just related to this complex SL2 triple in this way. Okay, so just so that you know what the notation means, because later on when I write down things for the period map, I will again use the n notation because this is a real SL2 triple. But as you hopefully realized, sort of to see how this SL2 triple emerges, it's a bit more natural to look at the L's. And also, if you want to do this simultaneous eigenspace decomposition, you need to look at the complex algebra. Okay, so as I said, the idea is now somehow to decompose everything in terms of weights with respect to the SL2 and charges with respect to this U1. And this was done first in Schmidt's paper. But actually, the mathematicians realized that you can do even better than this. And this was sort of the genius insight in this paper. Because what you want to do is you want to somehow use this SL2 structure as much as you can. So what they did is they said, okay, let's combine all three of these components, this L plus, L0, and L minus, into one big vector and write down a representation of SL2 that acts on this whole vector. In principle, what this is like a tensor product of the co-adjoint representation and the original representation you had. But the point of this is that it allows you to somehow mix these components further in a way that might become more useful to solve your equations. Okay. So at the end, what you do is you write down a decomposition of this phi, and we will attach three labels to it. So the lower label n just denotes its order in the expansion in y. Then there's this label d, which is essentially the highest weight with respect to the SL2 and how it acts on the individual L's. And then there's the label epsilon, which is like the weight associated to the representation that acts on the whole thing. Okay. And again, sort of the leading piece in this phi will be this SL2 triple that I already mentioned. So now you plug this decomposition into Nahm's equations, you pray a bit, and then lo and behold, you find a recursion relation, which we call the CKS recursion. So what is it saying? It is saying that these phi sub n's are determined in terms of phi sub k's with k less than n, right? So phi n is determined in terms of all the previous ones, which is a recursion relation that you want to have. So here this b is just some bilinear form, which you can write down explicitly, but it's a bit too ugly to put on the slide. Now, what I want to emphasize in this relation is that here on the right-hand side, it's not just the phi n minus 1 that appears, but it's all the previous phi's, okay? So this can be a very complicated expression, but you could put it on a computer and, you can go to as high order as you like. However, there's one issue, because there are some components that are left undetermined. And that is because this prefactor here on the left-hand side might vanish, okay? And that happens precisely when the indices take this form. So this we will call input data because, well, right now we don't know what it is. It's not determined by anything. And in order to go through the recursion, we somehow need to specify what this is. So what now? It seems like we are stuck, that we cannot really go through this procedure further. But remember that in the beginning of the discussion, when I introduced the period map, it was defined with respect to some reference Hodge structure, but I didn't really say much about what this was. I left this very arbitrary. So now the idea is going to be to pick a nice one, okay? And sort of the one that is screaming at you is this boundary Hodge structure. So it turns out, like I mentioned in the beginning, if you fix it to be this boundary Hodge structure, then you somehow get a compatibility condition between this period map and this boundary data that appears. In particular, I told you that there is this operator delta, and it turns out that this delta alone will fix for you what this input data is. Okay, I'm afraid I have to be a bit schematic here, because to really show how this works properly, I need to go into all the Hodge theory machinery, but I hope you will accept what I'm saying here, that somehow this delta will tell you what this input data is. And then from here, you are essentially done. You can put this into the recursion, you can find phi up to any order you like, and then from phi, you can somehow try to work backwards and find what this period mapping is. Okay? So the kind of results you will get is the following. So it looks like this. So let me go through it one by one. Again, there's this overall monodromy piece, which encodes the x dependence. Then there's a bunch of corrections which are fixed by this phase operator, okay, but a finite number of them. And then there's an infinite number of further corrections, which are all fixed by this recursion relation. Okay, and again, here this n minus and the n0 are this real SL2 triple. And just to show you what this condition looks like, so these GKs are determined or have to satisfy this matching condition with delta. Okay. And you see here that there's a finite number of them, because at some point this adjoint action of n minus will just be 0. So I have to admit, I think we understand quite well what this delta means mathematically, but a sort of physical understanding of the delta still sort of eludes me. So if anyone has any ideas about this, I would love to hear it. Okay, so now I have given you the main sort of procedure, and now I want to exemplify it a bit to make it a bit less mysterious. So as I told you, what is so good about this perspective is that this boundary data has been classified. So you can just write down what all the options are and go through them one by one. So in the paper, what we did is we looked at all 1 modulus weight 3 Calabi-Yau boundaries. This just means boundaries for Calabi-Yau threefolds. And you will have 3 options. You can have a conifold point, you can have a large complex structure point, and then you can have something called a Turing degeneration or a K point. And really, these boundaries are just distinguished by the kind of representation you have of this SL2. And here I'm just going to flash a table for you to show that it is really explicit. You can really, for each of these boundaries, you can just write down what are these SL2 triples, what is this boundary Hodge structure that is encoded in a charge operator, and what is the most general delta you can write down. Okay. So now just to show you a bit more, let's look at this type 4-1 singularity, which corresponds to the LCS point. The delta here will be given by this, and it involves a parameter chi. And this chi is essentially related to the Euler character of the Calabi-Yau, the mirror Calabi-Yau. And so this is very important, because it means that this delta encodes some information that at the end of the day will correspond to the 1 loop correction you get in the pre-potential for the period vector. Okay, so it contains alpha prime corrections. So now if you have this delta and you have the SL2, you can go through this whole procedure. You can write down the input data, put it into the CKS recursion, try to go through all the steps, try to give a general expression for every order. This is actually quite complicated, but we managed to do it in the paper. And then in the end, you can try to translate this into these corrections GK that appear in the period map.
Jeroen, sorry, you have 4 more minutes with questions. Okay.
Yeah, that's all right. I'm almost done. Thanks. Okay, so after this resummation, you put everything together into one big matrix, which becomes a horrible expression, but it is really explicit. can write down everything in terms of these functions. So this result looks horrible, but at the end of the day, you can really check that if you act with this on a boundary 3,0 piece, you get back sort of the period vector we know at LCS, which has indeed this alpha prime correction. So I want to emphasize that it is quite magical that this horrible looking real matrix acting on some boundary 3,0 vector, sort of everything conspires and cancels against each other to give you something that is holomorphic in the end. Okay, so that brings me to my conclusions. So just to summarize my talk in one sentence, I would say we have shown that it is possible to explicitly compute the nilpotent orbit approximation of the period map exactly from just simple boundary data that you associate to any asymptotic limit in the moduli space. Of course, there are many questions that still remain, like what are some applications of this? I did not say much about this, but the coefficients that appear in this period map are actually quite restrictive. And for example, Thomas used this in one of his papers to show the finiteness of self-dual flux vacua for the one modulus case. As I already alluded to, I would like to understand better what the physical meaning of this phase operator is. Maybe there's some relation with axionic strings. I don't have anything concrete here, but maybe there is. And I want to also emphasize again that somehow this theory is much more general than just Calabi-Yau. This works for any variations of Hodge structure. So I would be quite interested in maybe having some kind of string theory application where this becomes useful and you have to go beyond Calabi-Yau. Okay, so that brings me to the end of my talk, and I thank you for your attention.
Thank you. Thank you, Jeroen, for your very nice talk. We have very little time for questions, but maybe for some quick questions from the audience. Yes, Fabian, you can.
Thank you very much. Just very briefly, so that I make sure I understand. So initially, you had the equation, then you made some assumption, put this in the form of a Nahm's equation. This didn't make any reference to the reference Hodge structure. You got the recursion relation, but now the recursion relation that you got out of this procedure doesn't fix uniquely the boundary data. So now you somehow need to put the reference metric back in. So where was this dropped? At which point in the sequence that I was just talking about, when you got rid of the boundary data of this delta map, did you make this non-unique? Because it sounds like, yeah, in this step procedure of sort of going from your data to the to the recursion relation. I couldn't tell in your talk where the approximation was made.
Okay, so I'm not sure if I understand correctly what you mean, but sort of the place where this delta becomes relevant is sort of in this step, where I mentioned that you fix this reference Hodge structure to be the one at the boundary. And then you find that sort of compatibility with this delta fixes some of this input in the recursion, which you otherwise would not be able to fix. Does that answer your question?
No, it doesn't, but I'll ask you later. Maybe.
Okay.
Thanks so much.
Maybe you can also ask on Slack.
Yeah, or maybe the room can be kept open for a few minutes.
Oh yeah, sure, that's also fine. Yeah.
Thank you.
Thanks.
Okay, so I think we should stop here. Thanks, Jeroen. I will stop the recording.